Hello and welcome. It is my great pleasure to introduce Dr. Channing Prend from the University of Washington today. Channing did his undergrad in Earth Science and Mathematics at Columbia.
Yep.
Then went on to do a PhD in oceanography with the famous Lynn Talley and Sarah Gilly. And then has now been awarded a NOAA Global Climate Change Fellowship and is splitting his time between Caltech and UW, working with Andy Thompson and Georgi Manacharya. He has worked a lot on bio-ocean interactions, phytoplankton blooms, etc., and the influence of oceanography, physical oceanography on that. But will tell us today more about how ice and oceanography, in particular circumpolar deep water around Antarctica, interact. Warm welcome, and please take it away.
Thank you, Joe, for that last minute.
That was really good.
Amazing. So I'm excited to be here. Thanks for having me, and thanks for coming. So today I'm going to be talking about ice-ocean interactions in the Antarctic, which is a pretty broad, encompassing title because I really just want to talk about two pretty separate projects that I've been working on. But they both are related to ice-ocean interactions, although when we talk about ice, there's two very broad categories of ice that are quite distinct, which is ice sheets and sea ice. So ice sheets is referring to ice that's formed on land through the compaction of snow, so this contributes to sea level rise, whereas sea ice is formed from the actual freezing of the ocean water itself. So that's part of my broad title being just ice-ocean interactions. The first project I'm going to discuss is about ice sheet dynamics, and the second project is going to be switching gears to talk about sea ice variability. So just to give like a bit of an outline, as I mentioned, I'm going to be talking about two pretty separate, somewhat distinct projects, partly because these are both sort of hot off the presses, a new work from the first year of my postdoc, and I'm just sort of curious to hear people's thoughts on them because I haven't actually really presented on a lot of this work. So feel free to stop me at any point if you do have questions during the seminar. But I'm going to kick things off by first talking about the Antarctic ice sheet. So I'm going to be talking about pathways of ocean heat transport towards that ice sheet. So why do we care about the Antarctic ice sheet? Partly because it's losing mass very rapidly, and that contributes to global mean sea level rise pretty significantly. But the ice sheet is not melting the same everywhere. And so what this map is showing is actually an estimate of the melt rates, or really the mass loss from the Antarctic ice sheet from satellite altimetry. So places where Antarctica is red, like here along the West Antarctic, these are places where the ice sheet is melting more rapidly. So the ice sheet is really not melting the same everywhere. Why is that the case? That's kind of some of what I'm going to be addressing in this first portion here. So why is the ice sheet melting? It's actually primarily because of the ocean itself. So this is different from what's going on in Greenland and in the Arctic, where we have a lot of surface melt. But in the Southern Ocean and in the Antarctic, most of the melting of the ice sheets is actually driven by the ocean, specifically circumpolar deep water, as Till mentioned, which is a water mass that I'll talk a lot more about later. But this is a water mass that actually originates in the Antarctic Circumpolar Current here, which sort of circles Antarctica. So the Southern Ocean is quite unique, dynamically speaking, because it's the only place on the planet where there are no continental boundaries that impede the flow, which allows for the formation of a single current that actually circles around the entire globe, exchanging waters between the different ocean basins, as well as between the surface and the deep ocean. And so I really like this map projection, which is called the Spillhouse projection, because it really emphasizes the connectivity of the global ocean and the central role that the Southern Ocean plays within that global scale circulation. But within this ACC, we have mixing of different deep water masses from all of the different basins, which creates what we call circumpolar deep water. And that water mass is still quite cold, but 2 degrees Celsius about, which is warm enough to drive melt. So this circumpolar deep water is really the main source of heat that is supplying the melt of the Antarctic ice sheet. And so there's been a lot of work trying to look at where is that circumpolar deep water brought onto the continental shelf from the open ocean, and how does that vary in time? And so a lot of the work that's focused on the West Antarctic Ice Sheet, which again, if you remember from that map, is the ice sheet that is melting the most rapidly, a lot of that work has focused on looking at variability in these intrusions of circumpolar deep water onto the shelf and then eventually into these ice shelf cavities. And this is just sort of an example from Pierre Dutro's work, which showed that these wind anomalies at the continental slope can actually drive variability in this cross-shelf heat exchange, which then feeds back onto the melt rate variability. So we have some sense that the ocean variability itself is really important in driving the variability in the melt rates of the ice sheet. But this work is really all related to how we get circumpolar deep water across the actual continental slope itself or around the 1,000 meter isobab. But really this CDW is originating much further offshore in the Antarctic Circumpolar Current. So here's my kind of picture of why we have spatially varying mass loss from the Antarctic ice sheet. It could be due to variability in this first step, which is how does CDW actually make its way to the continental slope. Then there's also variability in the cross-shelf heat exchange, and then this shelf circulation that supplies heat to the ice shelf cavities. So any of these three sort of steps could have variability that's associated with variability in the melt rates, and it's not really clear which one of these steps is the rate limiting step. But I'm sort of going to be arguing that this first piece hasn't necessarily been addressed enough. As for whether it is the leading order important term within this sort of process, I won't really go that far. But I am going to be addressing this first piece, which is how does CDW actually make its way from the open ACC to the continental slope. And I'm going to do this using this model, which I'm showing here is the temperature on a specific density surface that corresponds to this CDW layer. So this model is called BSAUCI. So that stands for the Southern Ocean State Estimate, which is actually a data assimilating model. So it's a model that is actually constrained by observations using an adjoint, and it runs from 2013 to 2018. And so this map is just showing, so here's the Antarctic continent, and this is the mean temperature on this density surface. But now for the rest of this, I'm gonna just focus specifically on the West Antarctic area, because this is where the ice shelves are melting most rapidly, so it's certainly an area of interest. So if we zoom in on this green box, now here I'm showing a similar thing, so this is just zoomed in on that West Antarctic region. So we have three different marginal seas here, the Ross Sea, the Amundsen Sea, and the Bellingshausen. And this is still, the colored contours are showing the same thing as the previous slide, which is the temperature on this density surface corresponding to circumpolar deep water. The black lines that are sort of underneath here are the seafloor bathymetry. These pink arrows are the velocity field on this density surface. And then these brown lines are showing the approximate position of the Antarctic Circumpolar Current. So this one that's the most furthest south is sort of the southern boundary of the ACC. So this is the region that we're looking at, and we can see this sort of circle of cold water here that's expressed on this density surface from the temperature, and that's a signature of the Ross Gyre, which is a large-scale gyre that's forced by the winds that sort of characterizes the circulation in this region. And you can see, if you sort of follow these arrows, that we have the ACC moving to the east, but then we do have this southern flowing portion here, which is that eastern limb of the gyre. So this is kind of a schematized version of that circulation, where we have the ACC flowing this way. This is now sort of where the northern limb of the gyre meets the ACC, then starts to move southward, and then we actually have a bifurcation of the flow where it meets back up with this topography, where this is the continuation of the gyre here along the 1,000-meter isobab, and then here we actually have a separate stream of warm water that's flowing towards the Amundsen and the Bellingshausen. So the idea behind this work was to try to see how variability in this gyre circulation can feed back onto where heat is actually brought from the ACC to this continental slope. So how do we characterize the gyre and its variability? One way is using the barotropic stream function. So this is from the depth integrated velocity field in the model. So here, this green line is a specific closed contour of that stream function. This is the mean position of the gyre. all of these white lines are showing individual monthly realizations of the position of the gyre by the same definition. So we can see that there are certain places where the gyre varies more strongly in its position and other places where it's more constrained due to the topography. So here, for example, there's very little variability in the position of the gyre because it's very topographically constrained. Whereas here on the eastern limb of the gyre, once the gyre breaks from this Pacific Antarctic ridge, we now have a lot more variability in the position of where that eastern limb is, since we no longer have that topographic constraint until we meet back up with the seamounts here. And so that eastern limb is really of interest when we're talking about heat transport towards the ice sheets, because that eastern limb is what transports CDW southward from the ACC to the slope. And so if you're bringing that heat southward here, or all the way over here, that's going to change the distribution of where that heat is meeting the continental slope. So what I'm going to be arguing is that this gyre variability can modulate this offshore reservoir of heat that then gets tapped into by these cross-shelf exchange processes that other people have looked at. So first, what's causing that variability in the gyre that I showed? Well, we have some concept that the gyre is forced by the winds, as most gyres are, but it is a bit different in the Ross Sea here because of the fact that we actually have strong sea ice cover, which modulates the wind energy input into the surface ocean. So actually the quantity of interest in terms of the gyre forcing is what we call the ocean surface stress curl, which is equivalent to the wind stress curl in the absence of sea ice, but when ice is present, this is actually the expression mathematically for the ocean surface stress. So this alpha is the sea ice concentration being multiplied by the ice ocean stress, and then we have 1 minus the sea ice concentration being multiplied by the wind stress. So if the sea ice concentration is 0, this term is 0, and then we just have the wind stress. So if you just look in the model at the gyre strength, which I'm quantifying as the minimum of the barotropic stream function in this region, and look at it as just a monthly time series over this full model run, it's really quite well correlated with the ocean surface stress curl that's averaged over that central region of the gyre. So in terms of what forcings are relevant in leading to this gyre variability, it does seem to be the ocean surface stress. But that's, again, not synonymous with the wind stress, and it actually turns out that the sea ice concentration is pretty important in driving the long-term expansion of the gyre that we see in this specific model simulation. So that's the variability in the gyre itself, but now to try to illustrate what I mean about changing the location where heat is brought towards the shelf, here I'm going to identify these two different end member years, 2014 and 2018, within this simulation, as being sort of end member years reflecting a contracted gyre state in 2014 and also a weakened gyre, and then 2018 being an expanded and strengthened gyre. So this is just the full stream function, and we can see obviously these much lower values indicating again that the gyre is much stronger in this year. But if you follow this interface where you switch from blues to oranges, which we can think of as sort of the boundary of this eastern edge of the gyre, we can see that here this weakened gyre meets back up with the topography to the west of this seamount that's marked by this purple star, whereas here when we have an expanded gyre, we extend much further outward, which allows that heat that's moving southward along the gyre's eastern limb to be brought directly towards the Amundsen shelf. So now if we look at the temperature variability on the same density surfaces between these two end member years, so here red meaning that when you have a weaker and contracted gyre, you're actually warmer in this specific location when you're red. And we see this inverse relationship between the heat content of the gyre interior and the heat content on the continental shelf in the Amundsen. So this is reflecting some redistribution of heat within the system by changes in the circulation, rather than an actual temperature anomaly itself on this density surface, because the integrated heat content over this whole domain doesn't change that much on interannual timescales. So these on-isopical temperature anomalies are really just reflecting redistribution by these changes in the circulation. So that's sort of the contracted gyre state. It's associated with cold anomalies on the shelf in the Amundsen and warm anomalies on the gyre interior. And then we see almost the opposite pattern in 2018, which is that other end member year reflecting an expanded and strengthened gyre state. So here, this movement of the eastern limb further to the east that is characterized by this strengthened gyre, it's supplying more heat towards the Amundsen and leading to these warm anomalies here. I mean, at this point, I'm just suggesting that based off of these maps, but I'll show from some Lagrangian particle release experiments that I do think that's what's actually going on here. So now if we just take a transect moving offshore from, this is the location of Thwaites Glacier in the Amundsen Sea, which is often referred to as the Doomsday Glacier, or this is one of the most rapidly melting glaciers. And if we look at just a transect moving offshore from that specific location and look at the temperature anomaly on that transect between this weak and strong gyre end member year, we can see some indication that these anomalies that are occurring on the shelf are linked to some sort of larger scale anomaly that propagates offshore. So here when we have warm anomalies on the shelf in a stronger gyre year, that does seem to be linked to some sort of large scale anomaly that extends off the shelf. So again, trying to see how do these remote forcings of remote variability that are offshore actually feed back onto what we see on the continental shelf and with this melt rate variability. So now I'll try to demonstrate from some Lagrangian particle release experiments that these different gyre states are associated with strong differences in the percentage of particles that are moving towards this Amundsen sector. So here I released particles along this black transect, which is sort of corresponding to the core of that eastern limb of the gyre, and ran them forwards in time, looping the velocity fields from this contracted gyre year. So playing this thought experiment of what if we had, you know, an always contracted gyre, what would the pathways of heat transport, or really in this case just volume transport, look like? And so this is what you get when you have a contracted gyre. You move southward around these seamounts. You do have some amount of flow moving towards the Amundsen, but also a lot that's either being entrained into the gyre or moving towards the Ross. Now, if we do the exact same particle release experiment with the same release depths, which is throughout the CDW density layer, I'll show those depths later, and the same transect location, release location, but now loop the 2018 velocity field, so the opposite thought experiment of what if we always had the gyre fixed in an expanded state, and then we can compare where right off the bat you can already see just by eye from this subset of the trajectories that we have a lot more moving directly towards the Amundsen in this setup. And that's because of this extension of the gyre's eastern limb, which preferentially steers things to the east and less moves within the gyre circulation. So now if we look at the actual heat transport itself as a function of density through this release transect between these two end member years, we can also see that not only do we have more heat being steered towards the Amundsen in an expanded gyre year, we also just have a greater net southward heat transport through this transect. Yeah?
So just quickly, how long roughly time-wise does it take for one gyre rotation?
So this here is a 6-year integration time. It varies between, I would say, 4 to 6 years. So yeah, so these thought experiments aren't necessarily reflective of the real trajectories that any individual particle would take. I also have some other plots just from the full velocity field. But yeah, it is a multi-year, signal. So that's why playing this game with these end member years can be challenging in some sense, because really these are reflecting lower frequency processes. But this strengthened and expanded gyre is also just associated with a greater overall southward heat transport, which is primarily actually just due to the velocity anomalies associated with the stronger gyre rather than the temperature anomalies. But so when we have an expanded gyre, we have just a greater heat transport towards the poles, and then also this figure, what I'm showing on this axis is the release depth of the particles along this transect. And then this is the fraction of those particles that are released here that move towards the Amundsen. So when we have an expanded gyre here in red, we can see that in this upper circumpolar deep water layer around 400 to 700 meters, we have you know, almost half or 40% of all the particles being released here moving towards the Amundsen, whereas in a contracted gyre state, it's about half of that. So there is this significant difference in the partitioning of particles between these different pathways depending on these changes in the gyre state. And there's also an interesting depth dependence here as well, where it seems like the differences are larger in the upper circumpolar deep water layer. As we move further south, there's less of a difference between the different gyre states in terms of this partitioning, which is something that I'm still thinking a bit about. You know, the baroclinic adjustment of the gyre as opposed to the barotropic response, which is what I've been thinking about primarily. But if anyone has thoughts on that, I'm happy to talk about it after. So the main point here, again, is just that an expanded gyre is associated with a greater polar heat transport and also a redistribution of that heat with a preferential steering of CPW towards the Amundsen Sea, which is where, again, those most rapidly melting ice shelves are located. So that's sort of this first piece of the story. So I think this would maybe be a good time to stop if people do have questions before I switch gears to talking about sea ice. But hopefully this at least gives you a taste of some of this work. I mean, the main point that I'm trying to make with this study is just that this remote ocean variability that's actually quite far away from the ice sheet can still be important in modulating the heat transport towards the continental shelf. And so we do need to consider it within the context of understanding the basal melt rate variability, because there's really been a focus only on the cross-shelf heat exchange, which is certainly a necessary step in that delivery to the ice shelf cavities, but it's not the only piece of the story. Yeah?
So you have a pretty, like, on the time scale of your gyre circulation,
Yeah.
the amount of time you have is pretty short compared to that time scale. Do we have that much of an idea at all of the natural variability in those time scales?
Yeah, so there's a couple ways that people have tried to address that. One is to use dynamic ocean topography from altimetry to try to assess the gyre variability, which can be really challenging in these sea ice covered regions. But yeah, there have been a few studies. Tiago Dotto has a paper in 2018 looking at the Ross Gyre variability from altimetry, and they also show in that study at least that the portion of the gyre that varies the greatest in time is this eastern limb, again, because it's not constrained by topography. So it's consistent with that in terms of the magnitude of the changes in gyre area and strength that we see at interannual timescales in the model. They're comparable to what was shown in that paper from the altimetry. There have been a few like longer term climate model simulations that have been done for, like, you know, centennial scale simulations looking at gyre variability. One that just came out recently actually showed a projected expansion of the gyre into the 21st century because of this sea ice decline. So like I mentioned, that ocean surface stress curl rather than the wind stress curl is really what's important in forcing the gyre. And so if you have a long-term sea ice decline, that's going to increase the wind energy input, which will basically spin up the gyre. So in that paper for a centennial scale, they were projecting an expansion even further to the east from what I'm showing here, but that was a pretty coarse resolution model as well. But the magnitude of the changes are pretty consistent in this model with what we've seen from altimetry. But I should say this is a data assimilating model that also assimilates satellite data into it, so they're not really perfectly independent.
Thanks.
Yeah.
Yeah, I'm just wondering that what would happen if, because you mentioned that the CS and the floating CS does impact this gyre circulation. There's potential ice sheet collapse or like ice shelves going into the ocean also affecting, and then how, because it in turn affect the salinity, and then can they have like a major repercussions on the gyres?
Yeah, I mean, the meltwater, like the fate of meltwater from the ice sheets is really not well constrained at all from observations right now. So people are doing sorts of things where you use the TS properties from observations from instrumented elephant seals or Argo floats to try to see where is meltwater going. But the meltwater will impact the vertical stratification, which then can impact the gyre scale circulation. So there's certainly a feedback role where increased ice sheet melt could potentially lead to some sort of change offshore, but I think the meltwater is pretty confined for the most part to the actual continental shelf itself. Not so much of it makes it into the open ocean, so I don't think that would be of leading or importance to the variability in the gyre, but it's hard to say in the future. I mean, some of these projections for melts are pretty dramatic, and it's not clear where within those uncertainty bounds we're actually going to be, but if you really do, if we're at the upper end of those projections, then there is a potential that more of that meltwater can make its way offshore and actually affect the circulation off the shelf. But I think right now it's pretty unlikely that the ice sheet melt would actually influence the gyre circulation in any significant way.
Thanks.
So is the water in Ross Gyre actually warmer than the water in Amundsen Sea?
No, so the gyre interior has a signature of cold temperatures on this density surface. So the gyre itself, just the temperature values are much colder than what you have on the Amundsen shelf. So the Amundsen is what we classify as a warm shelf. So in the ice sheet community, people distinguish between warm shelves and cold shelves, which has to do with the bottom temperature on the actual shelf. And that is linked to where CDW is transported onto the shelf. So part of why the Amundsen is classified as a warm shelf, or really the reason that it's classified as a warm shelf, is because you have enhanced CDW transport there. But the gyre also does help to shield the Ross continental shelf from some of that warmer ACC water as well. So it's not just about what's making its way onto the shelf, it's also about what is this off-shelf reservoir that can be tapped into. So if you just compare a vertical profile of temperature at the 1,000 meter ice bath in the Ross and the Amundsen, you will see warmer temperatures in this CDW density layer in the Amundsen, even independently of any differences in the cross-shelf exchange. Any other questions? Yeah.
Yeah, I had one more on your last slide.
Yeah.
Just wondering whether, like, how deep does the gyre actually go, and whether there might be, you know, that convergence might also be something about
Yes.
strength, gyre strength.
Yeah, it's definitely something that I haven't looked into too much because I've basically been defining the gyre from the barotropic stream function, so I'm depth integrating the velocity field.
Right.
So I haven't really looked so much at the actual vertical structure of the gyre, but it does extend pretty deep. I do know that. I think it could extend all the way to 1,500 meters. But I don't have a great answer to that at the moment, but something to think about. Yeah, I mean, this convergence, one thing I was thinking about, that it seemed that particles that are in the upper circumpolar deep water layer get preferentially steered towards the Amundsen versus towards the Ross at this bifurcation point, regardless of the variations in the gyre. Like, that's true in all of the simulations, whether you use the mean velocity or any of the loop scenarios. And I'm not sure I understand why that would necessarily be the case dynamically speaking, but it does seem like there's a pretty strong depth partitioning in terms of what gets steered towards the Ross versus what gets steered towards the Amundsen when the gyre meets back up with the topography independently of any gyre variability.
Thanks.
Any other questions on this first section before I switch to sea ice? Great, well, I'm actually doing good on time, halfway. So now I'm going to switch gears pretty significantly to talking about sea ice. So this work is looking at variability of submesoscale dynamics in the sea ice zone, and I'll explain what I mean by submesoscale dynamics as we go on. So before getting to what I mean by submesoscale, I want to start at a much larger pan-Antarctic scale. So when we say sea ice variability, what do we actually mean by that? For a lot of people who are in the sort of CMIP, CESM climate simulation world, sea ice variability refers to a time series like this one, which is showing the sea ice extent anomalies for the entire Antarctic over the satellite record. And so this is a figure from Zach Labe, but you can see this really dramatic historic wintertime sea ice low that we've had this past few months, which is certainly alarming. But there's also a lot of insight that I've seen people presenting on recently that have to do with looking at variance in this sort of time series. You can see, for example, there seems to be increased variance as this time series progresses, which may be indicating a regime shift from dynamical systems theory. So there's certainly a lot of insight that has been and will, I'm sure, be gained from analyzing time series like this, but I do think it also can be a bit limiting to just have one single quantity as being representative of the total Antarctic sea ice state. And to try to illustrate that, here, this is just the average sea ice concentration from satellite data and anomaly just for July 2023, which was during this recent low. And so if we look at this anomaly map, we can see actually blue in a lot of the Amundsen sector that I was just talking about in the past presentation. In other words, we actually had higher than average sea ice concentrations across this whole sector, whereas everywhere else did see lower sea ice concentrations. So the point here being that sea ice concentration is actually reflecting atmospheric and oceanic processes that are occurring across a really wide range of scales. So if you just look at a single quantity like this, it's actually masking out a lot of this regionality that you can see when you start to dive into the data a bit more. And so now going to even smaller scales, if you actually just look at a satellite snapshot of sea ice concentration, which is what I'm showing here, here in the marginal ice zone, we see the reflection of eddies, fronts, and filaments in the flow. And so just from any single snapshot of sea ice concentration, the distribution of sea ice is actually primarily reflecting much smaller scale physical processes that are occurring at length scales here. Just for some scale, this is like order 100 kilometers here. So this could be a mesoscale eddy, but then there's also things happening at smaller scales as well. So how do we reconcile all these different scales of variability? Are these small scale eddies and fronts and filaments actually important in the context of these larger scale ice anomalies like what I showed from that sea ice time series on the previous slide, or is this all just noise that averages out over a large enough scale? That's a question that I'm certainly interested in. But again, just back to this idea of the scales of the ocean, is that really the distribution of sea ice is reflecting processes that are occurring from the planetary scale all the way down to the dissipative. And these scales are all interacting and exchanging energy and momentum, which is one of the things that makes oceanography in general just really challenging from both an observational and a modeling perspective. Because, for example, on the observational side, a lot of the traditional tools that we use, like going out on ships or using moorings, they're very limited in space or time, and so we're only resolving one small piece of the system, and so that's, I think, really fundamental to anything we do as climate scientists or oceanographers, because really any analysis of observational data has to grapple with the aliasing of variability at scales other than the signal that you're interested in. And then on the modeling side, we typically have this trade-off between spatial and temporal resolution, where these, centennial global simulations that are being used to make future climate projections have very coarse horizontal resolution, and so they're imperfectly parameterizing the effects of many of these key processes. Whereas these high resolution in space simulations are often confined to very small regional domains or short time spans and are being used for process studies. So actually upscaling the effect of those small scale dynamics to the larger scales is really challenging. So now I want to just introduce a little bit about what I actually mean by submesoscale before talking about some of these observations that I have. So dynamically speaking, submesoscale refers to motions that have Rossby number sort of around 1, the Rossby number being this non-dimensional parameter that tells you the importance of Earth's rotation for a specific physical phenomena. And these submesoscale motions are actually energized by a variety of instabilities that develop from the larger scale balanced motion. So Rossby numbers that are large are typically associated with geostrophic balance. So we have motions that are balanced, but that can have large buoyancy gradients associated with them. So that's one of the things that makes Earth or any rotating planet exciting to study, is that you can have what we call baroclinicity, which is where we have a misalignment between pressure gradients and buoyancy gradients or density gradients. And that can occur in a stable state in the ocean because of Earth's rotation. But when you have these large buoyancy gradients, like what is being shown in this schematic, then in that case we actually have a lot of available potential energy that's stored within that because the ocean wants to be mixed. And so when we're talking about submesoscales, one of the main instabilities is what we call baroclinic instabilities, which are feeding off of the potential energy that's stored in these buoyancy gradients that are occurring within the larger scale motion. But if you're not a physicist, or I've lost you from that explanation, we can also just think of submesoscales as having sort of order 100 meters to 10 kilometers, or timescales of hours to days. So that's sort of the approximate time and space scales that I am talking about here. But part of why these submesoscale flows are important is because they are ageostrophic, which actually allows for really large vertical velocities to develop. And so submesoscale fluxes are actually really important to the exchange of fluid and also tracers between the surface and the deep ocean. And so there's been a lot of work just in recent years arguing that submesoscale heat fluxes and nutrient fluxes can actually be important to these larger scale basin scale or even global scale heat budgets or nutrient budgets. But now coming to the ice zone, so as I said before, baroclinic instabilities are a really efficient mechanism for generating these submesoscale currents from the larger scale balanced motions. So they're extracting energy from the mean flow. And these baroclinic instabilities, because they're feeding off of these buoyancy gradients, they're quite common in the marginal ice zone because of the fact that you have a lot of strong lateral buoyancy gradients that are associated with sea ice melt and formation. And so the marginal ice zone, which is sort of areas with approximate sea ice cover 15 to 80%, those regions typically will have really strong lateral buoyancy gradients, and that provides an energy source for these instabilities to develop. And so this is some idealized numerical simulations from Georgi Minakarian, my postdoc advisor, showing that ice edge meltwater fronts can very efficiently energize submesoscale motions. And he showed, at least from these idealized simulations, that submesoscale heat fluxes can be similar in magnitude to air-sea fluxes from storms, again indicating that they may be important at these larger space scales and longer time scales. So the question that I'm really interested in with this work is, do these submesoscale fluxes, or small, intermittent, high-frequency fluxes, do they actually matter to the large-scale and seasonal or even interannual evolution of the ice edge, or is this all just noise that averages out? And so to do that from observations, I first actually need to introduce this parameterization, which is called the Fox-Kemper parameterization, which is a way of basically representing the overturning that's associated with these baroclinic instabilities. And the idea is to cast it in terms of this stream function, where this stream function, really the important point here is that it depends on m squared, which is the lateral buoyancy gradient, and it depends on this h, which is the mixed layer depth. So these two things together are what's setting that reservoir of available potential energy. And in terms of this stream function, we can also express an equivalent heat flux. So this is basically the submesoscale buoyancy flux, and this again just depends on the lateral buoyancy gradient and the mixed layer depth primarily. And so part of why we have to introduce this parameterization before I get to the observations is that it's not always straightforward to isolate a signal that's associated with submesoscale dynamics from some time series. So on the observational side, how do we observe submesoscales? One common way is from gliders. So this is an example of a time series of temperature, salinity, and then density from a glider in the marginal ice zone from Seb Swartz's work. And in order to observe the submesoscales, of course, we need to have measurements that have high enough frequency and small enough spatial scale sampling to resolve the submesoscales. But even once we do that, it's not necessarily straightforward to actually isolate a signal that's associated with submesoscale dynamics specifically, since this sort of a time series, again, could be reflecting processes that are occurring across a really wide range of scales. So that Fox-Kemper parameterization that I showed is one way of trying to isolate submesoscale dynamics from some sort of time series like this. So the idea is to take the lateral buoyancy gradient calculated from this along track density, gradient, and then plug that into the Fox-Kemper parameterization with an estimate of the mixed layer depth from the glider as a way of trying to estimate a submesoscale buoyancy flux from the observations. This is just one way of trying to isolate the submesoscale from observations. Another way could be to just divide the time series into different distinct frequency bands by filtering to try to isolate different time scales. That's another way of going about this, but the Fox-Kemper parameterization is at least dynamically based in the actual overturning that's associated with these instabilities, so it does have some sort of a dynamical basis as opposed to just using some frequency cutoff. But this is an example of, again, like the type of measurements that might be used to estimate submesoscale fluxes from observations. And really targeted glider campaigns are actually the main source of in situ observations from the Southern Ocean marginal ice zone that might be used to look at these sorts of questions. But the problem with this is that glider campaigns are typically targeted to very energetic regions, and they don't usually resolve the full seasonal cycle. So again, if you're trying to upscale the impact that these small scale processes play, it's really hard to do from this sort of data, because you might overestimate the importance of the submesoscales to the larger scales if you only have observations from really energetic places. So really my idea with this work, which is still quite new, really just what I've done in the past month, but the idea behind this work, or what I'm trying to do, is to characterize regional variability in these sorts of submesoscale fluxes. So to say, are there locations systematically that might be predisposed to having larger submesoscale buoyancy fluxes, and thus greater importance to the larger scale sea ice variability? So for example, if you have systematic differences in vertical stratification within the seasonal ice zone, as we do around Antarctica, that might lead to differences in the ability of these submesoscale fluxes to actually bring heat to the surface and melt the ice. But how do we actually go about doing that sort of a thing of assessing regional differences? Well, this is where I get to introduce some important collaborators of mine, who are these instrumented elephant seals. So these are elephant seals that actually have CTDs glued to their heads. Only for 1 year. When they molt, they fall off, so it's not a permanent thing. But so these are measuring temperature and salinity as the seals dive up and down in the water column, which is a pretty incredible data set, because here is just a distribution of all of the seal profiles from 2006 to 2021. There's over 1.5 million of them, and they're really the only observational data set that has high enough frequency measurements to even start to say anything about the submesoscale. Like things like Argo floats, they take a profile every 10 days. You can't say anything about the submesoscale from that kind of observations. So it is challenging, though, to separate spatial versus temporal variability from this sort of a data set. But these histograms are just showing the average, or just the distance between consecutive dives from the seals, and the time between consecutive dives from the seals. So on average, it's about 6 kilometers separated between successive profiles, and around 6 hours. So those sorts of scales are small enough that we can at least start to say something about the submesoscale. And again, this is really the only data set that has full circumpolar coverage where we could do this sort of a thing. So what I've been attempting to do so far is to actually estimate regional and seasonal variability of submesoscale buoyancy fluxes from this data. And I'll kind of just give a case study of one specific seal track as a way of trying to illustrate the methodology. But the idea, so here's a seal from the Bellingshausen Sea. So each one of these circles is the location of a CTD profile that's been taken by the seal. And then it's colored by the sea ice concentration that I matched up for satellites at the time and the location of the seal profile. And then the bottom shading is just bathymetry, and this is the maximum winter ice edge in purple. So here is an example of the time series of sea ice concentration from the satellite at the seal locations corresponding to this temperature profile that's collected by the seals, with this white line showing the mixed layer depth calculated from the seal data. So first, just as kind of a sanity check, was to show that actually the near surface temperatures measured by the seals are pretty close to the freezing point when the satellite is saying sea ice is present. So that's at least showing us that we do have some agreement between the satellite data and what the seals are actually measuring in the ocean. But then here, what I'm doing as a way of, again, applying this Fox-Kemper parameterization to the data, I'm actually estimating the lateral buoyancy gradient, which I'm calculating from the along-track seal density. And so the assumption that we have to make here is that the along-track gradient is primarily reflecting a spatial gradient as opposed to a temporal gradient, which may or may not actually be a good assumption. So I've been doing some work of subsampling a really high-resolution model at the seal profile times and locations to try to assess that. But yeah.
Can you just give a little detail on how location is measured and try like?
Yeah, so the location can only be measured when the seals come up to the surface, and then they have satellite iridium sensors.
There's no accelerometer on the...
No. Yeah, there's no accelerometer. So yeah, we only actually have their position when they surface. And so it's not really, it's honestly not straightforward to even get a profile out of this sort of observations, which again is another caveat and challenge that we have to deal with. But really, I'm not so interested here in the actual numbers of what we get as a submesoscale buoyancy flux because I'm interested in characterizing regional scale differences, you know, regardless of these sorts of methodological issues. The hope is that we can still identify some sort of regional scale pattern where we can say, oh, systematically in this location we have larger submesoscale buoyancy fluxes than we do in other places when you use the same methodology applied to the same data set, is the general idea. But yeah, I definitely agree that there are certainly challenges with this data set and with even just producing it in the first place, because the seals are not just perfectly going down and then going back up. They're usually diving and moving significantly as well, so assigning a specific profile is not straightforward.
Do we know, do they have like a typical dive angle or?
Yeah, I mean, that's what Fabian, who's one of the people that produces this data set, has a way of, I mean, that's how they come up with these profiles, is by assuming a consistent dive angle. But it's not really, that's not been very well constrained from actual observation, so they're just using one consistent dive angle, when it's pretty unlikely that that would be the case, because even if you look here, you can see that even for the same seal, the dive depth can vary pretty significantly over the course of the time series, because anything that's white here means that they didn't go that deep. And so it's probably unlikely that one dive angle would actually be reflective of every seal and every time of year and every location, but that's kind of the way that they have to go about doing it. But so anyways, this blue line is showing the lateral buoyancy gradient estimated from this one single seal track, and this gray is showing when CAS is present. And so the important point here is that we have this peak in the magnitude of these lateral buoyancy gradient fluctuations just before the ice forms and then just after the ice retreat occurs. So we have this strong relationship between the seasonality of the lateral buoyancy gradients and the actual ice itself. And this is because, again, sea ice melt and formation are actually what's causing these buoyancy gradients to form, so it's not necessarily so surprising that that would be the case. And then if we plug in that lateral buoyancy gradient, the blue time series, with the mixed layer depth into the Fox-Kemper parameterization to get an estimate of this submesoscale buoyancy flux, that's what I'm showing in orange. So we can see that, again, the submesoscale fluxes, or this QMLE, is peaking at the same time when the lateral buoyancy gradients are peaking just before the ice melt, or just before the ice formation and after the ice melts. And it's not, you know, shocking that there would be a strong relationship between QMLE and M squared, since the buoyancy gradient is literally one of the inputs into the QMLE calculation. But the reason it is a little bit surprising is that it's sort of been understood in other regions in the global ocean that actually the seasonality in the submesoscale fluxes, or this QMLE, is more strongly dominated by the seasonality of the mixed layer depth itself. So in the open ocean, we might expect that submesoscale fluxes would peak in winter when you have the deepest mixed layer depth, since that's what's setting the available potential energy for these instabilities. But in regions where you have really strong seasonal variations in the lateral buoyancy gradient, as we do in the marginal ice zone, there actually the seasonality in M squared, which is related to these sea ice processes, is actually what's dominating the seasonality in these submesoscale fluxes. So it actually is not a trivial result. But that was just sort of one specific seal. So now if I show here just a monthly climatology of the lateral buoyancy gradient and this QMLE, or submesoscale buoyancy flux, for all of the seals everywhere around the whole Southern Ocean within the marginal ice zone, we can see this sort of double peaked structure where we have the lateral buoyancy gradients peaking in fall and spring, again, when the ice melts and formation is occurring. So this is suggesting that even at the sort of circumpolar scale from all of this data, this relationship is somewhat holding up, where we actually have peak submesoscale fluxes occurring in spring when that ice melts, just following the ice melt essentially. And so that actually might be important for things like phytoplankton bloom initiation, because this is a re-stratifying process. So often ice edge phytoplankton blooms are framed just in terms of ice retreat increasing light availability to the surface ocean, which is certainly important as well. But there's also potentially a role that submesoscale re-stratification can play in bloom initiation as well. This also has implications for the overall contribution of submesoscale buoyancy fluxes to the overall upper ocean buoyancy budget, because they're peaking in spring, which is when you have a change in the sign of the air-sea heat flux. So air-sea heat fluxes are actually quite weak at this time of year. So you're having the strongest submesoscale heat fluxes when air-sea heat fluxes are the weakest. So that suggests, a potentially larger role that submesoscale fluxes might be playing in the actual heat budget or salt budget. So that's the seasonality and why it might matter. But then, again, I'm also really interested in the regionality, which I haven't had a chance to dive into too much, but just to get at this a little bit, here I'm showing just for the Bellingshausen sector, this is the location of all the seal profiles, colored now by this QMLE that's calculated from the Fox-Kemper parameterization. So anywhere where you see darker green colors is basically larger submesoscale fluxes. And there does seem to be a strong regionality where, like here, there's a really strong front associated with the Antarctic slope front or Antarctic slope current. Here we have the Antarctic coastal current. So we do see evidence of strong regionality that seems to be related to regions that are known to be frontal regions or boundary currents. So there's still a lot more to dive into in terms of the regionality, but just to kind of start to get at this, we can say, at least from a first pass, that there is a significant amount of regionality, which again is relevant to trying to upscale the effects of these dynamics to the larger scales using things like glider data. So I think I have 5 minutes, so I'll kind of just try to close up quickly so to leave time for a few questions on this work. But the main points I want to say from this second piece is that constraining this spatial and temporal variability of submesoscale dynamics is really necessary if we do want to upscale their impacts and try to see whether these are important to the larger scale or interannual variability in sea ice. And then it does seem like the seasonality of the submesoscale fluxes from this seal ice data, or seal data, is strongly modified by sea ice melt and formation. And that does have implications for trying to quantify their contribution to these larger scales. And so really quickly, I'll just give a few final thoughts, somewhat trying to connect these pieces together, which is just to say that both ice sheet melt rate variability and sea ice variability both are reflecting processes that occur across a really wide range of scales, and both local and remote forcings can be important. And really the multi-scale nature of these dynamics is part of what makes it really challenging and also exciting, both to observe and model these sorts of ice-ocean interactions. And I'll just kind of end by saying that I think untangling all these disparate scales of variability is important, because if we want to identify long-term trends associated with climate change or predict the response of the climate system to anthropogenic forcing, then we need to have a better understanding of what's actually driving this natural variability. And so I'm happy to answer any questions about this second portion or about the first portion as well. So thank you very much.
Thank you, Channing.
Yep.
Great. Students first. Evan, as per usual.
Yeah. So this is a question I have about the first part.
Yeah.
That I saved because I think it also includes what you're talking about in the second part.
Yeah.
But so you showed, I think, one plot showing the seasonal variability of the gyre itself, and I was wondering, so that the whole gyre is completely covered in sea ice for at least part of the year, right? And so what is the seasonality of the energy that is being input into the gyre? And I guess there's a little bit of a chicken and an egg problem as far as that extent of like, is the sea ice causing the extent to change, or
Yeah.
is the extent causing the sea ice to change?
Yeah. So the way that I basically tried to address that was by decomposing the ocean surface stress into just the ice-ocean component and
Yeah.
the wind component. And yeah, you're right. You're absolutely right that there's a really strong seasonality in that, because essentially the wind component contributes almost nothing to the ocean surface stress in winter because you have almost full ice cover.
Yeah.
And so there is an indication that as the sea ice starts to melt, and then you have it modulates not just the magnitude of the ocean surface stress, but it also modulates which of these components is dominating that.
Mm-hmm.
And in terms of like what that means dynamically speaking, I think it would be really interesting to think more about it. But I mean, the only way that I've really tried to address the difference between the wind versus the ice-ocean stress component was just by taking these two components separately and assessing both their seasonality and interannual variability. And it does seem like the strongest variability in the full ocean surface stress itself is actually dominated by the changes in the sea ice modulating the fraction of wind stress that's being input.
Okay.
So it's not, so this ice-ocean component is less modulated by the changes in the sea ice concentration than the wind component is.
So I'm surprised that the strength stays so steady throughout the year. Maybe it's just goes to show how much energy there is in the ocean, that it can be completely disconnected from the atmosphere for that long.
Yeah, well, I mean, the fluctuations in the gyre strength between a given year can be similar in amplitude to the fluctuations between years. So I think there is still pretty strong seasonality.
Yeah.
But the actual variability over time in the ocean surface stress curl does seem to be dominated mainly by the changes in the amount of wind stress that's being input due to the changes in this 1 minus CS concentration factor.
Yeah.
Like if you just look at the correlation between gyre strength and the wind stress curl, for example, it's not really actually that strongly related at all, which at first I was actually very confused and slightly concerned, because I was like, why is the wind stress not correlated well with the gyre? Like, it's a wind force gyre. So I actually spent quite a while even realizing that this was the problem.
Okay.
But yeah, if you just look at the wind variability alone, it's not really that reflective of the actual gyre variability.
Okay.
The surface, the ice water stress is an output from source.
Yeah, it is diagnosed in the model directly, but I don't really remember the details of where it comes from. I think it is just some constant drag coefficient that's being multiplied by something, but I don't remember what.
Because there's some interesting recent work, right, that this is not necessarily minimized when the ice, like it's not monotonic with ice concentration, because sometimes when you have low ice concentration, you might have a higher drag.
Yes. Yeah. And that's one thing that is less of a problem, I think, in the Southern Ocean compared to the Arctic, because actually the marginal ice zone in the Southern Ocean is pretty narrow. Or like, if you look at the ice edge itself, it goes from like 15% to 80% pretty quickly. So you don't have like these huge areas of reduced fetch and other things like that you see in the Arctic. But yeah, I mean, I'm sure that would be true. Or I mean, I would be shocked if that wasn't true.
Anybody else?
Great. Well, I think it's 1, and I heard there was a class after this. So, but I'm happy to answer questions over email or talk here as well. But
all right. Well, let's thank Jenny once more.